In this video, I would like to start a series of talks in which we analyze certain design features of a surface magnet brushless permanent magnet motor. And the topic today, the first topic, is really about the winding layout. This is the familiar chart of the classification of electric machines which we have used many times before. The motor of particular interest in this video is the surface magnet motor shown here, with sine wave currents fed from a three-phase inverter. Of course, it is an AC synchronous motor. This is not a complete design project because most of the main components are already given: the stator, the rotor, and the shaft. This is a common starting point for a new or revised design, and we can say that we are making the best use of existing components. The objective is to design the winding and then calculate the electrical parameters of the equivalent circuit so that we can estimate the performance. We can divide the winding design into two parts. The first part is the layout of coils. We have 12 slots and we're going to use 12 coils, so we will have 2 coil sides per slot. That is called a two-layer winding or double layer winding. We're not inventing anything new, but the example brings out a number of fundamental electrical principles which can be used in a more general context. The second part is the choice of wire size, the number of turns, the number of parallel paths in the winding. From this we can calculate the resistance, the inductance, and the generated EMF. And once we have this data, we will be able to calculate the torque and the power. The keen student might ask, if all the other components were given, why not the winding as well? Well, of course, the teacher must answer that it's necessary to do the exercise, so the winding has been deliberately withheld. But in a practical situation, it could happen that you are given most of the components and you are asked to design a machine with, let's say, a different number of poles. Here we're going to use 10 poles, but the same stator core, rotor hub, and shaft could also be used with 8 or 14 poles. Even the same coils wound around single teeth could be used, but the interconnections could not be reused, and that is what we're going to start with. This is what we call the winding layout, or perhaps the winding configuration. Although our ultimate focus is analytical, the first objective is to make a winding diagram that could be used in the winding shop or even in the factory. So let's just take stock of the main dimensions. The stator outside diameter is 120 millimeters and the stack length is 50 millimeters. The rotor outside diameter is 76 millimeters and the air gap length is 1 millimeter on a radius. The split ratio is thus 78 divided by 120, which is 0.65, and the ratio of the gap to the stator bore radius is 1/39. That is approximately 1/40th or 0.025. We need a convention for drawing coils. This is one possible convention. In the center diagram, we're looking at the stator from the connection end. In the little diagram at the top, the connection end is at the bottom, and I stick my head into the bore of the stator. I look at one coil. It has two coil sides and two terminals. I identify the go coil side, G, as the one that leads away from the connection end. In the center diagram, it's going away. The return coil side, R, leads back towards the connection end. In the center diagram, it's coming towards me. Of course, the coils normally have many turns. In the center diagram, we can see the end connections looping across. Top diagram shows only one turn. If positive current flows in the go coil side, a south magnetic pole appears on the bore of the stator between the coil sides. We can work this out by Fleming's right-hand rule, or the rules of electromagnetism expressed in vectors. You can use any familiar method as long as it's the right one. The little S and N diagrams help to confirm the magnetic polarity for current going one way or the other way around the coil. The green S denotes this magnetic polarity in the center diagram. Note that when we have a south magnetic pole between the conductors, the rest of the bore takes up a north magnetic polarity because the flux must go in closed loops. Since the area of the rest of the bore is much bigger, the flux density is much smaller in the outer regions. This is an example of Gauss's law. We'll see this formulated more precisely later. The diagram represents the direction of winding the coils. When we apply current, the direction of the ampere conductors is the product of the direction of the current and the direction of the conductors. In AC machines, the current typically has a sinusoidal waveform in time, so the ampere conductors alternate in direction and their amplitudes vary sinusoidally with time. The same is true of the magnetic fields produced by the ampere conductors. But of course the coils and conductors remain fixed in the stator. Before we leave this diagram, let's just note the positive direction, which is anti-clockwise. This is the mathematically positive direction, which makes sense here because we are taking a somewhat analytical approach. It's not necessarily the convention used in factories and winding shops, but here we will measure angles in the positive anti-clockwise direction, and that is also the direction of positive rotation. The slots are numbered on the inside of the stator bore, going anti-clockwise from 1 to 12. Note that we have a tooth on the horizontal axis, so the axis of coil 1 is on the horizontal axis at 0 degrees. That's quite an important concept which we will use several times again. Next we come to the complete winding, and here we have all the 12 coils, each one wound on a single tooth. This is sometimes called a double layer winding or two-layer winding because there are two coil sides in each slot. The number of coils is equal to the number of teeth, so it's equal to the number of slots, and every slot contains the same number of conductors. The coils are numbered on the outside, counting in the anti-clockwise direction. The coils are shown in the same drawing style as in the previous slide, but they are unconnected and there is no current flowing. This set of coils is sometimes called the primitive set in the theory of windings, and we will return to that concept later when we calculate the inductance. Our next task is to connect or interconnect the coils into three separate three-phase circuits with the correct polarities. This looks a little bit daunting even with only 12 coils, so we need an organized procedure. The procedure I'm going to describe here is very informal and even personal. I've tried to rely on common sense and of course a little bit of experience, but it's worth mentioning that there is an extensive theory of winding synthesis, especially in the older German literature and some of the very old English language literature. It is rich in the mathematics of integers, almost like the theory of numbers in pure mathematics. But this would be too powerful a tool to use here, and even if the winding layout were produced by a mathematical algorithm, we would still have to make many practical decisions. Curiously enough, many of those decisions would concern the interconnectors or jumpers, and they are factory decisions that would hardly benefit from a mathematical approach. If you ever have the chance to visit a winding shop, or especially a rewinding shop, I'm sure you'll see what I mean. To help with this sorting process, in this diagram the black arrows show all the coil axes in their actual physical positions in mechanical degrees. Also drawn are the rotor magnets, opposite polarities red and black. This rotor position, with the black magnet on the horizontal axis, is the reference or zero position. It's clear that coil 1 is perfectly aligned with a black magnet, while coil 7 is perfectly aligned with a red magnet. Both coils link the maximum amount of magnet flux, but with opposite sign. This means that we could connect coil 1 in series with reverse connected coil 7 to start building phase U. At this rotor position, no other coils are perfectly aligned with magnets in the position of maximum flux linkage. This connection is shown in diagram U1 at the top left, with the coil axis arrows of coils 1 and 7 colored red for phase U. The reverse connection of coil 7 is denoted by means of a dashed line. Now, as this is a three-phase motor, let's rotate the rotor by 1/3 of an electrical cycle, or 120 electrical degrees. A 10-pole rotor has 5 pole pairs, so 120 electrical degrees corresponds to a rotation of 120 divided by 5, that is 24 mechanical degrees. This takes us to the position shown at V1. Magnets have moved round by 24 degrees. We now find that coil 9 is perfectly aligned with a black magnet, while coil 3 is perfectly aligned with a red magnet, just as coils 1 and 7 were aligned with the same magnets 120 electrical degrees earlier. This tells us that coil 9 can be connected in series with coil 3 reversed to start building phase V, assuming the phase sequence UV. W. And again, at this position, no other coils are perfectly aligned with magnets. Now let us rotate the rotor by a further 120 electrical degrees to the position shown at W1, which is 48 mechanical degrees past the original reference position at U1. So this is 0, 120, 240 in electrical degrees. We now find that coil 5 is perfectly aligned with a black magnet, while coil 11 is perfectly aligned with a red magnet. So coil 5 can be connected in series with coil 11 reversed to start building phase W. Again, at this position, no other coils are perfectly aligned with magnets. Let's stop here to consider the conventional way of representing the winding, which we find in all the leading textbooks on windings and AC machines. We can see here phase U comprising coils 1 and -7, the minus sign denoting the reverse connection of coil 7. It produces a magnetomotive force, or MMF, which is maximum when the current in phase U is maximum. 120 degrees later in the time domain, the rotor has moved forward 24 mechanical degrees, and the current will be maximum in phase V, which comprises coils 9 and 3 reversed. At 240 electrical degrees in the time cycle, the rotor has advanced 48 mechanical degrees, and the current is maximum in phase W, which comprises coils 5 and -11. All this is represented in the MMF diagram. In the left-hand version, all the vectors are oriented in mechanical degrees. In the right-hand version, they are represented in electrical degrees. It is the right-hand diagram that is nearly always used, and in this form it shows immediately the familiar three-phase symmetry. The phase sequence needs to be carefully interpreted. Considering a three-phase set of currents applied to phases UVW with phase sequence UVW, the MMF will reach its peak value first in phase U, and then 120 degrees later in phase V, and then after a further 120 degrees in phase W. It appears then that the MMF progresses in the anti-clockwise positive direction. But these vector diagrams are not phasor diagrams. They are space vectors, frozen at particular instants of time. In all cases, the same value of current is implied because the magnitudes are the same. Under ideal conditions with sinusoidally distributed windings and pure sine wave currents, there is a resultant MMF representing the combined effect of all three phases, and that does rotate smoothly at synchronous speed. That is, in fact, the space vector of MMF, which is familiar in AC machine control theory. But we're getting ahead of ourselves. Let's go back to finish the construction of the winding. So far, we have decided the connections for only half the coils, the ones in the top row. At those positions, 0, 24, and 48 degrees, mechanical degrees, no other coils were in perfect alignment with a magnet. In the second row, at U2, we can see that if we rotate the rotor backwards by 6 mechanical degrees, coil 8 comes into perfect alignment with a black magnet, while coil 2 is in perfect alignment with a red one. So the series connection 8 minus 2 is in the same position relative to the magnets as the connection 1 minus 7 was 6 mechanical degrees, or will be 6 mechanical degrees later. This one is later than this one. And that is 30 electrical degrees later. Now, why did we do that? Well, we're looking for a way to incorporate the unused coils. And really what we've noticed is that when the coils are in the top group are perfectly aligned with magnets, the ones in the bottom group are only 6 degrees out of alignment, which is 30 electrical degrees. We could position the rotor so that the top group are misaligned 15 electrical degrees ahead, while the bottom group are misaligned 15 degrees behind. Maybe 15 degrees of misalignment either way is tolerable if we want to connect all these coils in series. Of course, if we have some experience of AC windings, we will know that plus or minus 15 degrees is not at all excessive. Indeed, the most common AC induction machines have a phase spread of 60 electrical degrees, which is twice what we're considering here. The same process can be applied to phase V and phase W. So in phase V, when the rotor is turned back 6 degrees from the 24 degree position, we find coils 4 and 10 in perfect alignment with the black and red magnets. And in phase W, when it is turned back 6 degrees from the W1 position, we find coils 12 and minus 6 in perfect alignment. We can now put the MMF space vector diagram together with all 12 coils accounted for. We can also go one step further, which is to connect all the coils of phase U in series, and likewise with phase V and phase W. When we do this with the same current in all 4 coils in any phase, the vector diagram gives us the resultant MMF of all 4 coils acting together. The diagram shows the physical orientations of all the coil axes in electrical degrees. Since the coils in one phase carry the same current, the diagram also shows the MMF vectors of all 3 phases. In each phase, the 4 coils combine to produce a resultant MMF, which can be constructed using the parallelogram. And its magnitude is 4 times cosine 15 degrees. If all the MMFs were aligned, the result would be 4. So the ratio of these two is 4 times cosine 15 divided by 4, which is 0.9659. It is the effective distribution factor of the winding at the particular harmonic, the working harmonic, which is the 5th. Strictly speaking, the MMF diagram refers only to the 5th space harmonic of the ampere conductor distributions of the respective phases. This winding produces many space harmonics of MMF, which we have tacitly ignored. The way we've ignored them is by switching between mechanical and electrical degrees as we study the orientation of the coil axes and figure out the best way to combine them. The vectors which we draw in mechanical or electrical degrees greatly simplify the process. In fact, if we did not adopt such a drastic simplification, that is, considering only the working harmonic, we would easily find ourselves lost in the complexity of the harmonic behavior of the winding. This is the right thing to do, however we set it up, because the essential operation of any AC machine centers on just one space harmonic, the one we call the working harmonic. In this case, it's the fifth mechanical harmonic, but sometimes we refer to it as the fundamental on the grounds that it is the first electrical harmonic. We still have to complete the winding diagram. So let's go back to the diagram of primitive unconnected coils and add the star of MMF vectors, which summarizes our decisions about the connections of the coils. Later we will see that the connections can be represented by a connection matrix, but what we need here is a practical winding diagram for the winding shop. So let's translate this into such a diagram, taking the phases one by one. And in fact, we've done everything that we need to do. All that remains to do is to make the drawings. So here we have the drawing connections for phase U. Coil 1 in series with 2 reversed, so it's 1 minus 2, and then minus 7 and 8. You can see that we've used a short connection between two nearby coils, leaving only one long jumper or long interconnector between the two groups of coils. Of course, we will have to bring these terminals closer together for the terminal box, so we will have another long connector in this region. And here it is for phase V, 9 minus 10 minus 3, 4. And here it is for phase W, 5 minus 6 minus 11 and 12. When all the phases are put together, the winding diagram looks like this. I think you could take this to a winding shop and they would be happy to wind it. They might find it a little bit fussy, too much artistic detail in the representation of the coils. Generally speaking, winding shops work with rather stark diagrams without so much color and detail. Now, this diagram represents the MMF distribution of two coils having the same number of ampere conductors or ampere turns located opposite one another. And we're going to use this to have a look at the harmonic properties of the winding. This could refer to coils 1 and minus 7, one of which produces a rectangular pulse of MMF and the other one a similar rectangular pulse of MMF 180 mechanical degrees away. This is mechanical degrees along the bottom. The width of each of these so-called pulses is 30 mechanical degrees, which is the angle between the center lines of the slot openings on either side of each coil. That is the slot pitch angle. In this discussion, it simplifies matters quite a lot to consider pairs of coils, opposite coils with equal ampere turns, because this eliminates even order harmonics and even a homopolar component that would arise if we considered one coil by itself. Now what we do is to resolve this periodic function into its harmonic components by Fourier series analysis. And I've mentioned this many times, but the Fourier series should be used here and not the FFT. The Fourier series analysis gives us an infinite number of odd harmonics, and before we do anything else we want to pick out the fifth. Here it is. We can see that it has 10 poles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 5 north and 5 south, just like the magnets. Indeed, it is this harmonic component of the MMF distribution that synchronizes or locks into step with the magnets to produce torque. And in this sense we have a classical synchronous machine. It's a little bit counterintuitive to think of all the harmonic poles of MMF interacting with all the 10 poles of the magnets. Surely the harmonic poles of the MMF are fictitious, except possibly at the physical locations of the coils. Are these not just a figment of the mathematician's imagination? In fact, we need the fifth harmonic MMF components from all three phases, because the fifth harmonic wave from one phase alone is stationary in space, merely pulsating in synchronism with its alternating current. It's only when we put all three phases together with a three-phase set of sine wave currents that we get a rotating fifth harmonic component. The peak value of that rotating component, by the way, will be 3/2 times the peak value of any one phase. The amplitudes in the diagram have been scaled so that the fifth harmonic amplitude is 1. The normal fifth harmonic coefficient for this waveform would be 0.1230 if the rectangular pulse had a peak value of 1. But the reciprocal of that is 8.13, which explains the scale. Since the fifth is the working harmonic, it's natural to normalize everything to that harmonic. And there is enough information here to take the design almost to completion, because it will give us the fifth harmonic winding factor, and that enables us to calculate the fundamental EMF and the torque constant. At the same time, we will be able to find the copper losses, which are related to the peak value of the rectangular MMF and not the fifth harmonic. Let's add a few more harmonics. Here we have harmonics 1, 3, 5, 7, 9, 11 and 13. The fifth one is the one we've been talking about, and it's shown in this heavy grey line with an amplitude of 1 per unit, if you will. All the others are scaled relative to this value. The most crucial point to remember is that it's the fifth harmonic that locks into step with the rotor magnets. Mathematician's imagination or not, that is how it works. So this is a very, very practical, important engineering concept. Regardless of the mathematical complexity, it's that fifth harmonic which really counts in the operation and the production of the torque. So we call this fifth harmonic the working harmonic. All the other harmonics cause parasitic effects such as torque ripple and eddy current losses in the rotor if it has any conducting components like the magnets themselves or a retaining sleeve or even the shaft. The size of some of the other harmonics comes as a surprise. It certainly shook me the first time I saw it some years ago. The idea that a machine could be operating with harmonic MMF components significantly larger than its working harmonic is quite a shock. The idea that a machine should synchronize with a harmonic much lower than some of its larger harmonics is quite a shock. The lowest order harmonic is in fact the two-pole harmonic, P equals 1, which is the first mechanical harmonic. Evidently, this is a subharmonic if we regard the fifth mechanical harmonic, as the working harmonic or fundamental. In fact, when the three phases are working together, the first mechanical harmonic, MMF, component rotates in the opposite direction to the fifth. And the same is true of the seventh harmonic, this one. We can also see the third harmonic and the ninth. This is the third, and then the ninth is in here somewhere. We tend to ignore the third and the ninth on the grounds that in a three-phase machine under balanced conditions, they cancel. Under balanced conditions, if there's any imbalance, the third harmonic may well be large enough to cause trouble in the core in the form of torque ripple or other parasitic effects. The higher orders, the 11th and 13th and so on, are becoming smaller as their order increases, and so we may be able to ignore them as long as they don't coincide with the mechanical resonance or cause excessive eddy current losses somewhere. Also, it's important to note that this analysis is for one pair of coils in one phase, really just the first row of connections in the earlier slide, giving us a 6-coil winding with one coil side per slot. When we add the second row of connections, we will find that the fifth harmonic is reinforced while many of the others are attenuated. Anytime a winding is spread out or distributed more, we expect to see a reduction in the harmonic content. That's not a very precise statement, but in general we expect that. Another important effect of the winding harmonics is that they contribute to the so-called harmonic leakage inductance, which increases the overall inductance of the phase windings. And that has been very important in the 12-slot 10-pole motor, particularly in relation to high-speed operation where field weakening requires, or flux weakening requires, higher inductance. Anyway, the final message is that the basic operation of the machine is based on the fifth mechanical winding harmonic, the working harmonic, and all other harmonics contribute parasitic or second order effect. They do not participate directly in the production of average torque. This is the bio slide as usual. Thank you for listening.